Welcome to the integration problem series number 2. This problem is also taken from the same book that I used for the problem 1, Pure Mathematics for Advanced Level by Bunde and Mulholland. I'm using a blue color now, Bunde and Mulholland, 1967. Okay, so in this problem, what we are given is, we are given this. Minus 1 to plus 1, the limit, square root of 1 minus x divided by 1 plus x dx. And we have to prove this as pi using the substitution x is equal to cos 2 theta. Okay, so let's go about doing this. So if x is equal to cos 2 theta, then dx would be negative sine 2 theta. That's the derivative of cos theta, and then we have to look inside what's inside the cos, which is 2 theta. So the derivative of 2 theta is going to be 2. So it's going to be minus 2 sine 2 theta. Okay, so now let's look at the square root here. So one of the ways in which you can get rid of the square roots is to take not the complex, sorry, it's the conjugate. So square root of 1 minus x divided by 1 plus x is same as square root of 1 minus x times 1 minus x divided by 1 plus x times 1 minus x. So what I'm doing is I'm taking the conjugate of 1 plus x, which is 1 minus x, multiplying and dividing by the same conjugate, which is not going to affect the value, so which will make our lives much easier. So it's going to be 1 minus x whole square divided by 1 minus x square. So now substituting for x is equal to cos 2 theta, so what we get is a nice little expression. We get 1 minus cos 2 theta whole square divided by 1 minus x square, which is 1 minus cos square 2 theta, which is same as 1 minus cos 2 theta divided by 1 minus cosine square theta 2 theta is going to be sine square 2 theta. So then write the whole expression something like that. So which, when applying the square root, it nicely simplifies to 1 minus cos 2 theta divided by sine 2 theta. Okay, so let's so we've taken care of the square root, we've taken care of dx. Now let's look at the limits. So when x is equal to minus 1, what's happening? When x is equal to minus 1, cos 2 theta is minus 1. So cos 0 is 1, and cos is negative in the second quadrant. That means it's going to be pi radians. So cos of pi radians is going to be minus 1. So 2 theta is pi, so theta would be pi over 2. So the second one is, what is plus 1? So we've got x is equal to plus 1, then cos of 2 theta is plus 1. We know that cos of 0 is plus 1, so 2 theta is equal to 0, so theta is equal to 0. So we've got the limits, we've got all the species within the integral. So let's go about substituting them and see how we're going to solve it. So we got integration, so from minus 1 to plus 1. So the minus 1 was pi over 2 to plus 1 to 0, and then the square root term, it nicely reduced to 1 minus cos 2 theta divided by sine 2 theta, and then the dx was minus 2 sine 2 theta d theta. So which simplifies very nicely as, let's take the minus 2 outside, it's going to be d theta minus cos 2 theta d theta, applying the limits. So that's going to be minus 2 So the integration of d theta is simply going to be theta with the limits 0 to pi over 2 minus, so the integration of cos 2 theta is going to be sine 2 theta divided by 2 with the limits 0 to pi over 2. And right away we see that sine of 2 times 0, that's going to be 0. Sine of 2 times pi over 2, that's going to be pi, that's also 0. So actually this whole term here, the sine 2 theta, applying these limits, this whole term is going to be 0. So let's look at the theta term here. So it's going to be minus 2 theta. So the upper limit is going to be 0 minus 2 times of minus pi over 2. It's going to be pi. So that was what we are asked to prove, and we nicely proved it.